Welcome back. This lesson's about a kind of old school concept, which is the percent dissociation for an acid. And the reason I think that this is a little bit out of style is that dissociation is not linear. You can't be sure that 5% of an acid is going to dissolve full stop because it depends on the concentration of the acid and how much pre-existing hydrogen there was. The acid dissociation constant just handles this a whole lot better than percentages do. But percents do exist, and let's see if we can calculate some. Here we have a solution where a certain amount of acid was dropped into water, and some of it converted into hydrogen, this much. You can make a percentage out of that by saying I got 1 times 10 to the negative 4 hydrogens out of 0.1 potential hydrogens. Every one of those acids could have released a hydrogen, it's just most of them didn't. And if you want to turn this into a percentage, you then multiply it by 100%. And if you do this, you get, that becomes 1 times 10 to the negative 3, multiplied by 100, you get 1 times 10 to the minus 1, which is 0.1% dissociation. So from this acid, 0.1% of it actually dissolved, the rest of it just remains as undissolved acid. Okay. This one is very similar. We have an amount of hydrogen, we have an amount of acid, so again, we just make a fraction out of those. 2.5 times 10 to the negative 2 divided by 0.5, multiplied by 100% if you want to turn it into a percentage. And that gives us, divided by 0.5 times 100, 5. So 5% dissociation from this one. Okay, this one is a base. So they tell us an amount of base, and every one of these bases could dissociate and give us an OH ion, but then they give us pH. We have to be careful here. This is a measure of how much acid there is in the solution, and this is a base that we're talking about. We don't want to combine those carelessly, or we will get in a whole heap of trouble. If the pH is 8.47, the pOH is 14 minus that, which is 553. I care about that because the hydroxide concentration is 10 to the minus pOH, so it's 10 to the minus 553, which I will now calculate. 10 power 5.53 negative. I get 2.95 times 10 to the negative 6 is the hydroxide concentration. Now that we have this, we can make a fraction out of it. We can say I have 2.95 times 10 to the negative 6 hydroxides out of, there were 0.01 potential hydroxides, and multiply that by 100% to get a percentage, and from that I get 0.0295% dissociation for this base. I've been a little lax talking about significant digits. These numbers had 3 sig digs, so I should be giving 0.100 for that. 3 sig digs here, so that 5 should be 5.00 technically. Here, this pH only has 2 significant digits, the decimals, and so I can't give 0.0295. This should be rounded to 0.030. So I apologize about this A and B. It looks like I was a little casual there. C, it looks like I got it, and let's hope I did D correctly so I can at least get up to half right. What do we have for D? D is the same trap as C. They tell us the quantity of a base, and then they tell us the amount of pH, which is an acid measure. So again, if pH is 9.6, the pOH is 14 minus 9.6, which is 4.4. Our hydroxide concentration then would be 10 to the minus 4.4, 3.98 times 10 to the minus 5 moles per liter. And so our percent dissociation is the amount of hydroxide we got divided by the amount of hydroxide we could have got, 0.5, if only they had all dissolved for us. Multiply by 100 to get a percentage. And that gives us 0.007962143%. This has 3 sig digs, this has 3 sig digs, so we would trim this off at 0.00796. The zeros aren't significant, but these 3 digits are. Super useful? I wouldn't think so, but hopefully not too bothersome either. See you next time.